Hey, it is hard to believe we've made it to the last week. Well, 3 more classes, right? Today, Wednesday, Monday. Today is the last class that I would consider new material for the final. All right, today we'll be doing a couple of different data structures. We will not be going into lots of detail on them, so they're going to have kind of overview type questions that I can ask for them. And then Wednesday we'll be doing the Comp 40 preview. So for anybody planning on taking Comp 40, I would strongly suggest you come to that. If you're not taking Comp 40, you can still come to class, and I think you'll get something out of it. It's not like I'm not going to do anything. I'm going to be talking primarily about how to prepare for Comp 40, but we're going to talk in detail about a couple things you might want to know. You can come to that, but you're certainly not required to. And then next Monday, we'll have a review class on this semester. OK? Any questions about that? No? OK. I just sent out a note on Piazza about the final exam. Our final exam is Wednesday the 17th, I think it is, or 15th? Is that the 17th? Wednesday the 17th? Yeah, that's it, 17th. The other exam, they'll both be in here, by the way. I got it switched, so they're both going to be in here. You're welcome to come to either one if you want to get your exams out of the way a little early. You can come to the early one, which is on Friday the 12th. Is that it? Yeah. So you're welcome to come to that one. Or you can come to this one as well, obviously. And I would just ask that I will send out a little note. If you're going to come to this one, just let me know. You can, but I just want to get a feel for the attendance just to make sure. I think this room's big enough for either class to be in here with some extras. OK? All right. Anybody know who this guy is? No, you're close. You're close. If I could speak. What did you say? Donald?
Well, it said his name.
Oh, it said his name. So you cheated. I see. Donald Knuth is his name. And he's actually one of the most famous computer scientists ever. He's a brilliant, brilliant guy. I'll show you a little clip about him later. He talks about this, one of these data structures we're going to talk about here. He's a legend in the field of computer science. So we'll get to him in a few minutes. OK. All right. Let's see. Here's what we're going to do today. So first of all, I did put provide up for song search. It seems to be working all right. I've gotten a couple people saying that maybe there's a couple little things issues with it, but for the most part, it's all right. Please take out any reporting you have other than the results of your search. In other words, when you load it up, you know how if you have, I guess there's a Boolean true in there that says whether or not it's going to print what song you're up to. Take that out. So make it false. So that it shouldn't, you should type song search and then the name of the song, the database, and then nothing should happen until it's ready to go. Does that make sense? So just take that out. I don't actually test for that in provide, but we will when we do probably will when we do the main one. So take that out. Let's see. So how many people noticed that there was that I put an online tester, like an online song search online? Yeah. So here's what it looks like. Where did it go here? Hang on. Move Donald Knuth out of the way. And here it is. I made sure the icon was recognizable as nothing you've ever seen before. But what this is so what I've got my version of song search running on a computer in my office, and the website here queries it with your searches. OK? And you guys know about log files. So does anybody know how Google makes their money? Google makes their money through ads, right? They make most of their money by selling ads to people that go up on the web page, and when you click on them, Google gets money, and they make billions of dollars that way, right? Now, how do they know that they want to send me an article for nerdy computer stuff, or an ad for nerdy computer stuff, and Ethan an ad for like nerdy poli-sci stuff? How do they know that? What do? They have cookies, but they basically, when you type a search, right? If I type computer, right? They're going to log that, and they're going to then feed me searches or ads that are based on the things that I've typed in for search. And they also have fingers in other websites I go to, and other people sell them data, and there's lots of ways to do it. Yeah? And they call your email. If you have Gmail, they look through your Gmail and whatever. They say they have pretty good privacy. I kind of believe them. How much do you really believe them? I don't know. But they have pretty good privacy. But some of you guys who figured out or who saw the Piazza post about this didn't realize that I also keep logs of these things, right? And some of the things you guys search for, all right? I'm just saying that I would advise against searching for things you don't want your professor to see, because there's a log of all of it, and it says exactly what you searched for, and some things you probably wouldn't be too proud of if I called you out on it. So anyway. Song search. This will work. It's for whatever reason it was slow at first. It's relatively fast now. That was the search, and it just prints out this is the full database. If someone wants me to put the smaller database on there, I'd be happy to do another version which just has the small database. I can do that. But yeah, this is it. I mean, it basically lets you search, and it's online and whatever, and that's that, right? What would you search for, Ethan? Poli-sci?
I
don't know.
That's not how you. All right.
Iceland?
Poly, like there's multiple, but it's political. All right, there we go. That's good.
There we go. Poli-sci, P-O-L-I-S-C-I?
Yeah,
Is that it?
Yeah.
One hit. Yeah. Anyway, so yeah. So feel free to use this to test to make sure that your full database search is working as well as ours, because I don't test the full database on provide. It just would take too long for you to try to do provide if you did that. Okay? Questions on this? The blue's a bit different in the S and the G and the A. Try to get the font right, but the blues are different. Okay. All right. Let's go. Any other questions about song search at this point? Anything else? Let's do what? Sunday? Coming up. Hopefully you got a little bit of time to work on it over break. If you didn't, keep working. All right, we'll try to have lots of TAs in the office this week, and at the end, as the week kind of ends, I'll try to spend more time in the labs. So if you're having any burning issues. Nothing? All right. Okay, so here's what we're going to talk about today. We're going to talk about two more data structures. The first one we're going to talk about, and both of these data structures are based on other structures you've seen. In fact, both are based on tree structures. But again, they're the kind of data structures that people won't necessarily expect you to know. But if you do, and you like pull one of these data structures out during an interview, that might be impressive. Just because, who knows? They might say, hey, that's a pretty neat use of such and such. Okay. The first one we're going to talk about is this thing called a rope. Okay. Now, a rope is a data structure that's used in place of strings. Okay, so if you had a string like this, the quick fox jumps over the dog. Okay, if you had this string, in memory, that's going to be just laid out in order, right, contiguously in an array somewhere. Right, that's how strings work. So they're fast in that sense. They're laid out in memory contiguously, but there's problems with that arrangement. Okay, can anyone think of maybe, not problems, but something that might be kind of slow to do for a string like this? What do you think, Cecily? Raise your hand. Just kidding. Cecily, go ahead.
Maybe if there are a lot of repeated letters.
If there's a lot of repeated, oh, I see. So if you're saying if there's a lot of repeated letters, maybe it's like not a good use of space?
Yeah.
That might be true. That's kind of another topic altogether, like a compression sort of idea. And some programs do keep their strings compressed in memory because it tends to be just as fast or roughly as fast to keep them compressed and decompress them as you're doing it, especially if you've got a big database that you only touch parts of at various times. That wasn't what I was thinking of. Ethan,
I was thinking if you wanted to insert in the middle.
not Ethan, sorry.
Do a lot of moving in your array.
Yeah, if you want to insert somewhere, right, if you want to say the quick brown fox, right, if you want to put brown in there, then you're going to have to move all this. And not only are you going to have to move it, but what if your array is only this big? You're going to have to do what? You're going to have to expand it, which means move everything. And it's not the most efficient in that sense, right? Adding to the end is easy. Adding to the beginning is not easy. Adding to the middle is not particularly easy. But there's some issues with strings. And what we're talking about here are not tiny strings like this. This is a really small string, right? I mean, it's 32 characters long. That's not bad. But what if we're talking about, well, where would you see lots of big text strings? Any idea, Mackenzie? No? Where have you, what's that? Yeah, where would you see a lot of text strings? You guys haven't done a dissertation before, have you? Go ahead. Where do you think? Any publication, right? If you're doing a book, right? If you're typing in your word processor, let's say, right? And the word processor has your entire book in it. Like, do you think they store that as one long string? I don't know, probably not, right? They've probably got some other data structure under there that's storing it. Maybe they store it by paragraphs, or maybe they store it by sentences, or something like that. But they've probably got something else under the covers. Because if you're going to keep one giant long string, it's going to be somewhat inefficient to do these things, right? It wouldn't be good if you had your whole book and then you decided to add the table of contents, and as you were typing, every letter took like a second to do because it had to keep like moving all your data, right? That would probably be bad. So they've got to do they probably do something else. Well, one of the things they do is this thing called a rope, right? And what a rope is, well, we already talked about this. You have to break the string if you want to recreate the new strings if you want. What a rope is it's this interesting data structure where it takes your string and puts it in tree form by parts of your string, generally very small parts or somewhat small parts. Okay? So it makes this table or this tree up, and it just breaks the string into various parts. Now the parts, if you're creating it from one giant string, you can make it so that it's even. Like, so this one would have just about as many characters as this one and this one. But let's say that I've been inserting and deleting. Maybe you end up with something like this. Okay? Over time, you might end up with something roughly like this. Okay? And so you keep it in this form. Notice where all the words are. Where are all the words in this case? At the leaves. OK, so all the other nodes are overhead. So there's some overhead in there. But there's these numbers in there. Can somebody think about this? Talk to your neighbor. See if you can figure out where those numbers come from. You already got it? So where do they come from? What's that? OK, so where's this 19 come from? Where's the 24 come from? It is weird. See? A little harder than you thought. I'm going to make you think for this. I know, it's not that easy. You'd think it was. That's why I asked you. I mean, it's not that hard, but it's not that easy. OK, if you figure it out, try to figure out why we do that. OK, we'll first talk about what the actual strategy is. So where do these numbers come from? OK, where does the 10 come from? Anybody know? The length of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. OK, easy. 6 is the same thing, right? Where's this 10 come from? What is it? It's the left. OK, where's the 24 come from? All of the left, right? 19 and 5 is 24, right? So the size of this is, if it's a leaf, it's just the size of the characters in there, right? If it's not a leaf, it's just it's whatever's in its left-hand piece, okay? And there's a reason for that. It's not like we just throw these numbers up here. Think about why that's the case. If now you know that, think about why. Talk it over. I want to see you guys think. I know we've got one more week of class, but think. You got to figure it out, Isha? Isha, you got to figure it out? No. OK. Sam, what do you think? Sam, what do you think?
From left to right, so is that why you're storing everything to the left?
Maybe. Good job. You made that up. Good job. What do you guys think? Any idea? What's that? Stuck. All right. Anybody think they have it figured out? Oh, nobody does. All right. Oh, Graham does. OK. And I know you haven't seen this before because in my video anyway, because I didn't do this last year. There you go. All right. All right. Graham's going to try to explain this one. Go.
So if it's a leaf, it's just the number of characters in the string.
Yep.
And if it's not, it's the number of characters in its total left
Yep.
tree, which is if you're looking for a specific character, that tells you where to go.
So if we're looking for, pick a character to look for. Which one? Oh, some character number 8? OK. So if we're looking for 8, all right, then we're going to start at 16. And which side does it have to be on if 16 is the number of characters in the left, if we're looking for character 8? It's got to be this way, right? Same thing for the 10. OK? Now you've got 10. So if it's got to be the left of 10, it's got to be down here somewhere. Once you get to this one, is there anywhere left to go? So you better just count over 8. 1, 2, 3, 4, 5, 6, 7, 8. There's the C. OK? So 8 was an interesting example. I would call that almost a corner case. OK? What's a different example? Give me another number, higher number. Yeah? 15. OK. So 15. What are we going to do here? Go left, because it's less than. OK, what are we going to do here? OK, we're going to go right. But if we know that 10 of them are that way, how many are going to be left on this side based on what we're looking for? 5 more, right? So if we go down here, now we're at 5. So we subtract the 5 from here. We get to here, and we've got 5. And what's 6 related to 5? It's actually more. So we would go left, but there's nowhere left to go. So if we can't go left, then what do? Count over 5? 1, 2, 3, 4, 5. It's the n. And what was the number again? It was 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's the n. See how that works? So these numbers are there so that it gives us enough information to quickly do a search for a particular position. If you want to search for an actual letter, you just have to you have to walk through in order and do the search. I mean, there's no other real way to do that. But if you want to search for a particular position, that's the easy way to do it. You just use the numbers up here to your advantage. Make sense? Kind of easy. This is not a hard data structure in that sense. OK? The weight of a node is the length of the string plus the sum of all the weights in its left subtree. And it's tough to see that, isn't it? Hang on. It's a little better. A little better. OK. So this is in this case, I searched for 21, which is exactly the same thing, right? 16 is less than 21, so we go here and first subtract 21, so we get, what do we get, 5. And then 24 is greater than 5, so we go this way. Greater than 5, go this way. 1, 2, 3, 4, 5. That's the J, which is the 21st letter. Make sense? Not a hard thing to do, really, in the end. OK? All right. So that's searching. What other things do you think we could do with ropes? Yeah. We can concatenate strings, right? By the way, this is the full algorithm. These are one-based, by the way, which is, if you were thinking, hey, wait a minute, that doesn't make sense if you're looking for 0 or something. If it's one-based, right? You should be able to do that. But that's the algorithm. It's a recursive one. It's pretty simple. Pretty simple. OK. So Max says, let's concatenate. OK, concatenation is easy. Right? Concatenation is so easy. You take 2 strings or 2 ropes, create another node, tack one on the left, one on the right, and you're done. The one that's going to come before the other one. So if you want to concatenate hello my and then name I, then you would just take another node, a new one, and you'd stick it on there. And you would calculate the left-hand side. And in this case, it's 9. And then the right side's done. So it's an order 1 operation, except for the fact that you do have to calculate the weights here. So it's going to be order log n, because you might have to go down here, more or less 1/2 log n, because you don't have to go to the other side. And we're going to assume these are relatively balanced trees. There are other balancing algorithms that we're not going to get into, but they're more or less balanced. Okay. What else could we do? If we can concatenate a string, what else do you think we can do? Maggie? Yeah, break apart, right? Split a string. We could do that. I think that's the next one, yeah. We can split a string. Splitting's a little bit tricky, right? If you wanted to split like on Simon, right, you would just go whoop and split right there, and that's an easy split. If you want to split right before the me, it's a little bit trickier. You got to find this like position to go down, and everything basically to the right going up of this one needs to be split off. Okay, so you split, and there's a couple things you need to change. What has to happen to the right-hand side when you split? What do you think? One thing that needs to change on that side. Does the 2 need to change? No. The 6, does that need to change? Yeah, because it's the left-hand side. We just chopped off 4 of them. So this is going to change to what? It's going to change to 2 because this one's going to be gone. So that's going to change to 2. And then this side, what do we have to do with this side? Concatenate these two, right? So we just put another node in there, slap the node k onto the left side and node h onto the right side, recalculate that if necessary, and we're done. Well, calculate the other one up here. OK, pretty easy. Not too bad. Update the left node, which is d, to 2, and then just concatenate the other 2 with a new root, and we're done. And now we've got 2 ropes. OK, all right. So let's see. We've concatenated. We've split. What other things can we do? Ever hear of cut and paste? OK, what's the paste? Insert, right? So we're going to have to insert into here, right? And inserting, I don't actually have a diagram for this one, but inserting is an operation that you can do with the 2 other operations we already came up with, right? To insert into a tree, first you have to do what? Let's say you're going to insert it right here. What do you have to do? Split, right? And then concatenate twice. Concatenate onto this one, and then concatenate it all back together again. But you've already got the functions to do that, so it's not so hard, right? Complexity on that is also log n. So we're talking about some logarithmic behavior here, and it makes sense. They're all trees, so it's generally going to be logarithmic, right? But you can do this with split and 2 concatenates. OK, we've talked about cut. Or we've talked about paste. What about cut? What would that entail? If you're going to take out a little part, or delete, I should say, what would you have to do for that? Yeah?
Split and then just do 1. Or no. You would have to do 2 splits.
2 splits and 1 concatenate. Yeah, you split the piece out that you want, you throw it away, and you concatenate the rest back together. Good. OK. So that's that. Again, no picture, but it's the same idea. Basically, you can do it with 2 splits and a concatenate. Easy. OK. And then finally, so let's say that you're doing this text editor and you wanted to print the document. What do you actually have to do with all those ropes? Yeah. You have to traverse it. So how are we going to traverse a rope? What order are we going to do? Post order, pre-order, level order, in order? What do you think? Yeah.
Would it be an in order, but you only print the leaves?
You only print the leaves, yeah, but it's in order. Sure. Yeah, it's going to be in order. Why is it going to be in order? Because you're going to want to print this one. And then you're going to want to go over and print this one. Remember, in order was you go to there, you print it, then you go back, and then, and so forth, right? So you go, and then on the way back up, you print, and then you go to the other side. So go down, print, back down, 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 and the way back, print, down, print, and then print. And that does the quick brown fox jumps over the lazy dog. And that's that. So that's another way to do that. OK, so it's not that hard. Not hard to do. None of these operations are particularly hard. In fact, I bet you could implement a rope fairly quickly, right? I'm sure you could write all the rope algorithms you want on the final exam. No, I wouldn't make you do that. Not make you do that. But you might want to talk about some of the operations on the final exam. But I wouldn't make you write them. OK? Questions on those? Yeah?
How do you decide where to put the string?
Well, it depends what you do. It depends where you are. Let's say you have a cursor or something, right? And let's say somebody wants to like cut, and they've got a cursor here, and you know the end is going to be down here somewhere, right? You have to like know where to cut, and then you do that.
No,
Yeah.
I meant like when you're originally making.
Oh, when you're originally making, yeah, that's a good question. So what kind of balance do you really want to have on this? Any idea? Like you don't want the quick brown fox jump over lazy on one node and then dog on the other, right? What would you want? You want them to be pretty much balanced. So you want them to be about what? Like half and half, right? Yeah, so basically the first two nodes you want to be half and half. And if you want to make it deeper, you just make each one of those about half and half and about half and half, as deep as you want. I mean, you probably don't want to make them 1 or 2 characters. That seems a little ridiculous. But I mean, making them 5 or 10 characters is fine. I don't know the general idea of what the minimum you want to make it. I haven't seen anything particular about that.
Exactly.
No, and it doesn't have to be necessarily half and half. And this is like after I've done some things to this, right?
Okay.
So yeah. Okay. And I guess we didn't even talk about this, but if you do want to cut out something that's in a node, what do you have to do? Yeah, you just go down to this one, find it, and then just cut those pieces out of that one part of the string. So it's not really that hard. Okay. All right. What are some advantages to ropes over strings? What do you think? Maggie, you just answered everything today.
It's faster to insert.
Definitely, yeah, it's faster to insert, unless you're like at the end or something, right? Yeah, OK. So that's good. It's easier to do some of those other functions we talked about. They're always logarithmic, it seems, so that's good. And logarithmic is not perfect, but it's better than n, especially if you're talking about giant text documents, right? OK, what about, what do we say right at the beginning? Strings are normally what? They're stored how? An array that's, so it's all next to each other. So what happens if you're dealing with a 4 GB string? Yeah, it's kind of like one of the quasi benefits of linked lists, right? Every node, you just add a little tiny piece. You don't have to have a huge amount for the whole thing, right? This suffers somewhat from some of the same downsides. I mean, you've got discontinuity, so it doesn't help in caching and some other things. But it's generally less. It's better in that sense. OK, so what are the disadvantages? Yeah, go ahead.
Well, lookup for a string is O1 and not so for the row.
Lookup for a string is oh, you mean the actual location. Right. If you know an index. Yeah, you're right. You're right. So indexing is not so good. Yeah. OK, that's one of them. What else? Yeah.
Going to print it.
Yeah. Printing it's definitely a little bit longer. It's logarithmic versus just n. Yep. Yep. Or rather, I guess it would be n log n because you got to find it and then print the whole thing. So yep, that's true. Let's see. How about the fact that everything's stored at the nodes down here? What about the other nodes? Just overhead, yeah? Yeah, that's all overhead. OK. So those are a couple like downsides. But for the most part, a lot of editors, as far as I know, a lot of editors use something like this. And as I said, if you're doing Microsoft Word or something, or Vim or Emacs or something, you're probably not going to want to just store giant long strings. It wouldn't be very efficient. OK. All right, so this was a report to print it out in order. And then let's see if we got most of these. So rope advantages. Faster insertion and deletion. They don't require extra memory when operated upon. Yeah, that's, I guess, a different one. We didn't really talk about that one. But if you're just concatenating 2 strings, just boop, put them together. Otherwise, you're going to need extra. If you're going to concatenate 2 strings, you're going to need extra space to copy everything over. No contiguous memory. And this one's an odd one. If you don't only use destructive versions of operations, in other words, you don't actually when you delete things, you don't actually remove them. There's other operations you can do to kind of store them separately. You can use a rope fairly easily to do undo, which is kind of nice. If you're doing a whole bunch of things, you can do lots of undo. Undo is not a hard concept, actually. You just basically keep track of what you've done, and then you can roll it back by kind of doing the exact opposite. Like if you delete all the x's and you know where all the x's, you keep track of where they all were, and then you put them all back. It's not really that hard to do, but this is another benefit. OK, what are the downsides? Well, overall space usage, right? Parent nodes, they don't do anything for us as far as the strings goes. All right, memory versus time and trade-off there. Okay, there's some overhead. The bigger your rope, like the bigger amount of text you have to deal with, the less you have to worry about this overhead. Okay, the overhead just it kind of shrinks proportionately, which is kind of nice. You have to manage the extra storage. And then here's another one that you don't think of too often, but it's more complex. And the more complex it is, there's greater chance that you have bugs and so forth. OK? All right. So that's ropes. Yeah?
Why is the overhead order n?
Let's see. So you've got the leaves are always half the number of everything else. So really half of n is n. I think that's probably it, right? Because
So not like so they're saying n being the number of leaves.
yeah, it really could probably be the overhead's probably 1/2 n or something like that. But yeah, on the order of. OK, good. Questions on ropes? Like I said, I mean the kinds of things I'd ask you, I might ask you some of the disadvantages or advantages. I could ask you to talk a little bit about like how to cut a rope or something, but I wouldn't ask you to write any code about it because we haven't done any of that in practice. OK. All right. Any other questions on that? OK. Let's do this. I know it's already kind of early, but let's take a little break right now because the next thing we're going to do is the last thing, and it's a little intense. So take a couple minutes right now, and I've already seen some sleepy eyes anyway. So take a couple minutes right now, and we'll be back. So this is the last real data structure we're going to talk about. Now this is a biggie. A biggie in the sense of it's probably the most complex one we've talked about in a while. Okay? So first of all, I wanted to show you Donald Knuth talking about this. So as I said, Donald Knuth is, like I said, he's one of the most famous computer scientists ever. He didn't even know about really much about computers at all until he got into college. He went to what's now Case Western Reserve. Anybody from Cleveland? On here, yeah. Went to Case, and he actually in high school, he's really a math person, which is great because most of the algorithms that he worked on were very mathy type things. But in high school, he actually got an article published in Mad Magazine, a math article. Published in Mad Magazine. You'd think, why would they do that? But I guess they were a little more intellectual back then or something. But anyway, it was a funny one. I mean, had humor to it. But he also won a science fair competition where you guys know about bases, like math bases, right? Base 10 and base 2 and base 16 and all that. He came up with a scheme for doing an imaginary number as a base, which is really weird, right? It's like the base was like the square root of -2 or square root of -1 or something like that. So very odd. But anyway, he won a math competition that way. Got into college, saw the first computer that they had, some computer they had there, and kind of fell in love. And then his career took off. And since 1962, he has been working on a book. This is part of it here. Anyone know what the book's called? It's called what? It's not a murder mystery. It's a computer science book. It's called The Art of Computer Science. And it's hopefully, he says it's going to be 7 volumes. Right now it's about 4 volumes. It's like 3.5. I think the 4th one is on the table there, and it's almost done, or it's just been completed or something. And he's been working on it since 1962. He took about 7 or 8 years, or maybe 5 or 6 years off. Maybe it was even more, to basically write a typesetting document processing program because he hated the way his books were looking. It used to be that your books, when you typeset a math book, there was literally a guy who sat in front of a giant linotype machine and picked out the individual characters and put them down on the page where they needed to go. And you've seen those fancy math formulas where there's all sorts of math. Well, some guy had to by hand do this, and it looked amazing. Well, in the late 70s, version the second edition of his first volume or second volume or something came out, and they decided to use a computer to do it. And the typeset looked so bad because they hadn't figured out the formulas right that he said to himself, I can't handle this. Nobody's going to do it by hand anymore. I'm going to have to just do this program myself. He hired two summer students to work on it over the summer, and then 7 years later it got finished. and he finished it. So anyway, it's called TeX, or the version most people use is LaTeX, which is kind of got a bunch of easier things to it. But he writes in straight TeX, and all his stuff looks beautiful and whatever. But anyway, spent many years talking about this. And one of the things he wrote for this version is binary decision diagrams, which he became enamored with and wrote this whole stuff. So I'll let him tell you a little bit about that. And by the way, he is getting a little bit older, and his mind is all there, but he has to, he stutters a little bit and he wanders a little bit. But still, I think most computer scientists who are his level are a little absent-minded and so forth. I mean, it just kind of comes to the territory. But you'll see. Anyway.
Basically, I'm writing The Art of Computer Programming. I started it in 1962. And BDDs are somehow special in the art of computer programming because they weren't anywhere near on the scene in 1962. It's one of the only really fundamental data structures that came out in the last 25 years.
So think about that for a second. 25 years. This is about 5 years old, this video. So in the last 30 years, unless something's come up in the last 5 years, the only really fundamental data structure that's even been invented in the last 25 years are these binary decision diagrams. Most of the rest, all done, right? We've figured out most of the rest. The germs were there, but nobody
but it wasn't until 1986 when Randall Bryant published a paper explaining what a great new data structure this was and how many things you could do with it, that they sort of took part of the computer science world by storm. So there was no part in the table of contents of the art of computer programming that had anything to do with this data structure because it hadn't existed. Now, when I say taking it by storm, his paper for many of the last 5-10 years, his paper was cited more often than anything else in CiteSeer. According to CiteSeer, his was the #1 reference paper. That's partly because you had to cite his paper if you wanted to use BEDs because it wasn't mentioned in any textbooks, or very many textbooks. There were a few textbooks, but also because it's a great paper. And he had a great idea. So, but now, of course, I knew about. I think it was middle of '90s when I first heard about BEDs myself, because I was interested in Knight's tours.
So Knight's tours, he happens to be interested in chess. It's a way of moving chess pieces around the board. But anyway, he goes on for about an hour and 40 minutes or something, and it's a little tedious. But he talks all about these binary decision trees. So cute story. So this shirt he's wearing, you can't see it right here, but it says The Art of Computer Programming Volume 4. It's a shirt. His wife made it for him. Because she knew he'd been working on Volume 4 for a while, I guess. So anyway, yeah, so brilliant guy. Also a very good musician. Happens to own a pipe organ that's like in his house. I don't know what his wife thinks about that, but anyway, he plays the organ and does all these, writes a lot of other kind of books too. And yeah, he actually has a website. It's a really stark website, but it's a website that on there he says, look, if you want to contact me, you have to go through my secretary. You can email her or send her an email or send her a letter or whatever. He said, I don't do email anymore. I did email for 15 years starting in 1973, and then I stopped. So I don't do email anymore. So I don't know. That's the way he is. OK. All right. So that's Donald Knuth setting up our binary decision trees here. So what are these things all about? Well, first of all, we have to talk about Boolean expressions. How many electrical engineers do we have in here? A few? Few? Cecily, I thought you were a double E, no? No? Oh, you're just taking ES3. If you're a double E, you will know Boolean functions very well by the time you get through a lot of your classes because they are, if you're taking ES4 next semester, you will talk about these things like all the time. And ES4, by the way, I think is a really fun class. I love it. It's a kind of a cool class on digital logic. But Boolean functions are the cornerstone of a lot of things in computer science. Whenever we talk about Boolean expressions like if x is greater than 7, you're getting a Boolean response back, right? Computer engineering uses Boolean expression functions all the time for circuit design. Like you're going to design a circuit, you're going to need to use these Boolean functions to make sure to like design the actual circuit. Okay? What's nice about Boolean functions is it's binary math, so there's ones and zeros, and that's it. What's not so nice about it is that it gets really complicated really fast because things explode exponentially. All right, and I'll show you what I mean in a few minutes. OK? All right, let's start out talking about Boolean functions. Most of you guys should recognize this from either math class or Comp 61 if you're taking that, or some other math classes. Truth tables. There's a couple of functions here, simple ones. A and B, and A or B. OK, and here's the very simple truth table. And what it's doing is saying, look, here you just enumerate all the different combinations of A and B. And you say if they're the same, it's a 1. And if they're different, it's going to be, if they're both 1, it's a 1. And if there's any zeros in there, it's a 0. OK, and that's an AND function. Pretty straightforward. OK, does that make sense? 0 and 0, and is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. OK? There's also OR, right? And OR is kind of the opposite, right? It's like if either one of them is true, then it's true. So these are not like big, huge ideas. You kind of understand this stuff, right? What other functions for two variables do we also have? What other ones do we have? Yeah. Which one? Which one is that? We've got or. What other ones do we have? Yeah. We've got XOR, exclusive OR, which is what? A and B, and XOR, whoops, 0, 0, 0, 1, 1, 0, 1, 1. What would the exclusive OR function look like? So explain it. What is exclusive OR? It's when only one of them is true. So 0, 0, none of them are true. 0, 1, one of them is true. 1, 0, one of them is true. 1, 1, now there's too many that are true, so it's 0 again. That's exclusive OR. OK. We use exclusive OR. Actually, it's funny. It used to be that you would say exclusive OR like A and A. When you exclusive OR two things that are the same, what do you get as an answer? 0, right? This is an easy way of setting a variable to 0. In fact, if you're using assembly code, sometimes you would do that. And the reason you would do that, instead of saying like A equals 0 or whatever the equivalent is for registers and so forth, you would do it this way because this happened to be faster than doing this. So doing an exclusive OR was actually faster than setting it. So people would generally do this. I don't think that's true anymore, but they would usually do that. OK, so that's one of them. What other ones do we have? What else? Yeah, Erica. OK, there's not. Yeah, there's. You said A and not B. Let's just say not B. OK, not B. OK. If we've got this one, we've got A and B. 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1. OK, so not B. What would this one be? 1, and this one? 0, and this one? This would be 1, and this one? 0. Did it matter what A was? No, so it actually didn't matter at all what A was. There's actually two functions that don't matter what either one are. True and false, right? If it's true, it's just all 1, 1, 1, 1. If it's false, it's 0, 0, 0. OK, what are the total number of functions between two variables that we have? Is that what you're going to answer? Or are you going to give us another one? What's another one? NAND. That's a good one. That's actually a pretty important one, actually. What is NAND, Max? You what? Couldn't tell me off the top of the head. Anyone else tell me 0, 0, 0, 1, 1, 0, 1, 1. What's NAND? It just stands for not and, right? So if we and those two together, what do we get? 0. And if we do not of that, 1. And if we do this one, it's going to be, and is going to be 0, so it's going to be 1 again. And this one, 1. And this one, 0. That's an important one. As it turns out, I'll talk about that in about 1 minute. OK, but that's another good one. Yeah? Yeah, there's if A, then B. I think you might do that in might do that in discrete math, right? If A, then B, I forget, what do we actually call that? I forget. It's a, what is it? Implication, right? If you have if A, then B, then 0 for A always gives you 1 for some reason. I forget why. But 1 and then 0 would mean what? 0, and then 1 and 1? 1. So that's called implication. So how many total are there? Yeah.
16.
There are 16. Deanna, is that what you're going to say too? Or were you asking a different question? Deanna? You're good? OK. Yeah, so there's 16. How did you know there were 16 of them?
Because that's all the combinations of outputs that you have.
Yeah, all the combinations of outputs. There's actually 16 different outputs that you can actually have. OK, as it turns out, here's the 16 of them. They all have names, actually. I only put some of the ones up there. I think I got most of the ones that we talked about. Didn't get implication up there. But what it is for any k variables, in this case it was 2, you have 2 raised to the k number of combinations. That gets big really fast, right? What if we had 10 variables? How many combinations would you have? 10 to the what? Not 10 to the 100. Ten raised to the 10, or sorry, it wasn't 10 raised to the, it would be 2 raised to the 10 raised to the 10. What is 10 raised to the 10? A billion, 10 billion, right? 2, 1, 3, 4, 5, 6, 7, 8, 9, 10. That is a pretty darn big number, right? You're not going to ever store all those different combinations for 10 different variables, right? For 2, it's 16 of them. For 10, it's 10 billion, 2 to the 10 billion of them, right? That's a lot. OK? OK, so anyway, you can enumerate all those. Now, we're not going to use all of them, right? We're not going to use all of them. There's 16 of them. Why use all of them when you can actually just use one if you really want to? Turns out that NAND is an important one because you can make any of the combinations out of just using NAND, which is kind of neat. OK, what you can do is you say, all right, fine, this is NAND. We already went over that. If you want to get not A, you just do A NAND A, and that will give you not A. Because 0 and 0 gives you 1, and 1 and 1 gives you 0. And that happens to be not A, but it also is A NAND A. Interesting. OK, so you could do that. Anybody ever hear of an FPGA? You hear that? What's an FPGA? Do you know? It's configurable logic. What they make them out of generally is these things called NAND gates, which say, look, the whole chip, it's a chip full of these NANDs on there that can be connected in any way. And what you can do is you can configure them. In other words, you program them to be any circuit you want, which is really cool. Because then you can program it to be any circuit. It's going to be fast, and it's going to be pretty efficient. OK, it's hard to program those. That's the problem. Have you ever programmed any Verilog or whatever? What's that? Oh, that's what you do. There we go. It's not easy, is it? Now it is, maybe. You've probably done it long enough. But yeah, it's not an easy thing to do. But these are how FPGAs are built. They're all built with these NANDs because you can make NANDs into any circuit you want if you're talking about circuits. So that's kind of neat. But anyway, you can make not A. And then you can also do A and B pretty easily, right? First, you start out and you do A NAND B. And you get 1, 1, 1, 0. But what did we say AND was? 0, 0, 0, 1. So what do we have to do to this one? Not this one, right? So if we first do NAND on A and B and then take the output of this and do NAND again on that, we get not 0, 0, 0, 1. And that's A and B. So you see how this works? You can make any of these out of a NAND. Mackenzie, you're looking at me like I'm crazy. No? OK. But you can make these out of there. OK, this is all set up, by the way. All right, it's all set up. So what we generally do is we limit ourselves to 3 operations. OK, we limit ourselves to using not, and or. We forget about NANDs. They're a little hard to work with on their own. So we just make everything into not, and or. OK, and we already know what the truth tables are for that. And what we do is we represent them. By the way, we have kind of shorthand to represent these. OK, the shorthand for not A is just either A with a bar over it or A with a little apostrophe. That means not A. A and B is like AB. And by the way, it's very similar to multiplication, right? 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. It's kind of very similar in that sense. We also have a shorthand plus, which is for or. It's also kind of similar. 0 plus 0, 0, 1, 1. This one's not, but otherwise it's more or less the same. OK, but those are the shorthand. And we can start writing these Boolean functions using our shorthand. So this stands for not x1, not x2, not x3, all anded together, or x1 and x2, or x2 and x3. That makes sense? How that works? OK, like I said, you electrical engineers will get real used to this. With 3 variables here, the number of solutions to this, and this is different than the number of possible combinations. This is with 3 variables, there are 8 different solutions where each variable is either 0, 1, or 0. OK, let me give you an example. Let's say we said let's say that all 3 of those were 1. x1, x2, and x3 were 1s. What is not 1? 0. What is 0 and with anything? 0. So this part's got to be 0. Even though this is also going to be a 0 and a 0, but that would be 0. OK. What is 1 and 1? 1. So that's OR with this, right? And actually anything 1 ORed with anything else is also 1. So this whole thing has to be 1, right? That's one of those 8 combinations, right? The other 7 would be if you made like x1 1 and this one 0 and that one 1 or whatever. There's all those combinations. Okay? We could easily store the outputs as 8 values. Okay? What if instead of having 3 variables, we all of a sudden had 1,000 variables? Right? How much space would we need to keep this 1,000 variable, the output for this? 2 to the 1,000, right? You're not going to be able to do that. Okay, that's still a number way too big to even consider storing all the outputs. So what we're trying to do is we're trying to find a representation of this so that it's efficient and we can quickly find out all these different combinations. Okay? All right, this is another example of the same exact thing where we just figure out one of the solutions. You can look at that later. Okay? Here's one way to do it. Okay, we can do these things called a binary decision tree. And this is what happens. You look at the tree, and it's got a node at the top, one of the variables. And then it splits off. It has a false and a true side, a 0 and a 1 side. And then that splits into the second variable, which is now each of those have their own combination. So it splits again. This is how the exponential part comes about, right? Because it splits for however many variables you need. Okay? And so let's see if we can follow this. Before we used 1, 1, 1, and it came out to be 1, right? I think. If we go to the 1 side, which is the solid line, 1 here, and then 1 here, and then 1 here, we get to a 1. Right? Let's see if we can get to a 0. If we go 0, and then 1, and then 0. And that's part of the truth table, right? 0, 1, 0 gives you a 0. See how that works? So this represents this. And this does represent it. The problem is we haven't compressed anything at all. This still takes 2 to the n minus 1 nodes to do this. Right? There's nothing you can do about that because you've got to split, and you're in trouble. Okay? However, notice something about this. If we get here to x2 and we go to 1, does it matter what x3 is? x3, if it was 0, we get a 1. If it was 1, we get a 1. So this is kind of redundant. Once we get to here, we already know if we go 1, we're going to have a 1. So this piece is actually redundant. So that we can compress these things. And this is where binary decision diagrams come into play. What you do is you merge things. Okay? First of all, you merge any what we call isomorphic. And for our purposes, isomorphic just means the same. Any subgraphs which are the same, combine them into one. Okay, a lot of times this is going to happen at the bottom. When we have all those 1s and 0s, just whoop, right into it themselves. And we eliminate any node where its two children are isomorphic. So in this case, we can eliminate this x3. We can also eliminate this x3. They don't actually matter to this function at all. So what does it become? Well, you can actually get rid of the x3. Okay, so now you get to x2 and it's just 1 or 0 because you don't even have to worry about it. Okay, the other side doesn't actually change anything. The next thing you do, and this is the part where you go, oh, what are you doing to me? If you combine all these 1s and 0s into just 1, 1, and 1, 0, you have to do some funky moving of the things. So it ends up becoming this. It's not that bad. But really all it is saying, look, x2, 0 goes to 0, 1 goes to 1. x3, this x3, 0 and 1, etc. So it becomes more of a graph instead of a tree now. But that's what it becomes. Okay? All right. Now, the big question is, how do we actually create these? All right? There's a number of different algorithms. I'm only going to have time to show you one today. But going from this to this is not that hard, believe it or not. Okay? And you can do it fairly reasonably, going from this to this. Then going backwards is also not that hard. I'm just not going to have time to show you that today. But going from this to this is not that hard. Okay, and this is the part that we talk about. Now, in this case, we haven't taken away too many nodes because it's such a small diagram. But think about if it had 10 or 20 or 30 variables. If you get from this giant 2 to the 10 or 20, 30th, and you can shrink it down significantly and get something much smaller, you've got a win there. Okay, and that's what this is all about. Okay, this is called reduced order binary decision diagrams. We just normally call them BDDs, binary decision diagrams. Okay, it's a directed acyclic graph. Directed meaning it has arrows. Acyclic means there's no way you can go in a circle. And it's a graph. And the compression part is the part that makes it so that you can do cool things with it. The other nice thing is the only way you're allowed to do this is if from the x1, you're only allowed to go to x2 if you go to x2 on one side, you have to go to x2 on the other side unless it's been merged. You can't go x1 to x3 on this side, then to x2. That's not allowed because you want them to be unique. So that's it. But anyway, once you do this, it's compressed and it's nice. Problem is, the way you order the variables actually makes a difference. Okay? And by what I mean is, in this case, we went x1, x2, x3. Like we did it, x1's at the top, x2, then x3. If we chose some other way of doing it, you could end up getting really ugly. For a certain function, it's in the references. There's a function here. If you go x1, 2, 3, 4, 5, 6, 7, 8, it goes pretty simple, easy binary decision diagram. If you went 1, 3, 5, 7, 2, 4, 6, 8, you get this ugly thing. Right? So ordering ordering the variables is the hard part. And it turns out that ordering the variables is what's called NP-complete, which means it's not easy to do. Like the ordering of the variables, you basically have to go through all the combinations to get them right. But with this many, it's not so bad. There's a computer program that I may get a chance to show you, which goes through it very quickly. Okay? So anyway, bad variable versus good variable ordering. Okay? All right, how do we actually do this? All right, this is the part where you got to concentrate a little bit. Okay, and I'll try to go through it relatively slowly. Here's what you do. Let's say you have a function like this. A and B and C, or B or not B and D, or not C and D. Everybody get that that's the function? Okay. What we're trying to do is we're trying to convert that into a binary decision diagram with the following ordering. I don't know why they picked this ordering, but B, C, D, and then A. That's the ordering we're going to do. So first thing we're going to look at is B. Okay. What you do is this. You take your function and you say, you find these things called cofactors. And what it means is if you look at the function and a term has a B in it, you write it down without the B, AC. If it has a not B in it, you get rid of that term. And if it doesn't have any B's in it, you keep that whole term. Does that make sense? Pretty easy when you look at it, right? So for this function, it's going to be AC, because there's a B there, for the function cofactors with respect to B, and or not CD, because there's no B's there. So far, so good? If you do function with respect to not B, well, this one's going to go away because there's a B, but it's not the right kind. This one is just going to be the D, and this one's going to stay the same as well. Not C, D. Okay? And now we've broken it down into like two parts, and that's like the first division. Okay? You've got the first division, and you can do a graph that way, like this, right? You've got B, and then the two C's, and then what we're going to do, well, I guess that was in the last one. Well, what we're going to do now is we're going to do the same exact thing with respect to C. We're going to take those two pieces and do the same thing with respect to C. So we started with A and C, or not C and D, and we're going to do this with respect to C. Well, this one's going to be A, because the C is going to go away, and this one's going to go away because it's C, not C, so that's going to go away. So you're left with A. And then with respect to C, not C, this one's going to go away, and this one's going to become D. See how that works? OK, you do the same thing with the other side, and it ends up being D when you do B prime with respect to C, or not B with respect to C, because this one goes away and it just leaves a D. And then this one's an interesting one. This one ends up being D because there's no C's there. And this one, because it's a C prime, it just also becomes D. But what is anything ORed with itself? It's the same, so it's just going to be D. So now, here's the interesting part. You've got you've got 4 different nodes here, but 3 of them are exactly the same. If they're the same, merge them. Okay? If they're on the same level, or if they're in the same piece, I think these two, not B, not C, and yeah, these two are the exact same, so we can actually get rid of this, right? And make this a D instead of a C, because we can actually get rid of it. So what happens you end up with changing the graph run and getting rid of that whole kind of piece. And then this one also goes to D, so we make that one go to D too, which is kind of nice. Okay. And what we're left with is we have to figure this one out and these ones, and you just do the same process again. Okay, you do the exact same process, and you end up with a decision tree that looks more or less like this, and you still have to do this one. All right, and this one has to be with respect to A, and so A with respect to A is just 1, and so that's going to be like that, 1 and 0 like that. And this is what it ends up being. So that 4 variable 1, which would normally have 2 to the 4th number of nodes, right, which is what? 2 to the 4th is 16, would have, sorry, is that what it was, 2 to the 4th? Yeah, 16. Then it now becomes one of 1, 2, 3, 4, 5, 6 nodes, and it's nice and compressed. Okay? Questions on that? I mean, I know I went through that really fast, but the point is that it's not really that hard to do once you figure out, oh, I just have to do these cofactors. Anybody ever done partial differential equations? You'll get there someday. It's scary, but it's the same idea, right? Doing things with respect to other things, it's the same idea. Okay? All right. So when you look at the truth table, this binary decision diagram came up with this, creates this truth table, and we can check it for various ones, right? Let's check it for this one, 0, 1, 1, 0. So you start with B, which is goes to 1, and then C, which is also 1, and then A is 0, and there we go, 0. And 0, 1, 1, 0 is a 0. You see how that works? So it's this decision diagram created that, it represents that truth table. Okay? All right, so why do we even care about this stuff? Like, why am I showing you this crazy diagram, right? Well, first of all, you can program it into a computer, right? This is the online one, right? We use it in a number of different ways. We use it for CAD software. So computer-aided design for circuit diagrams, right? You plug in your circuit, and you say, hey, I want to create this, and it will plop out the circuit by doing a similar type of analysis, right? It also allows you to actually verify whether or not the circuits that you've created are doing exactly what you want. So it's nice to be able to do verification and creating of these circuits. So electrical engineers and computer engineers use them all the time. And then finally, this is the one that they said, this is from Wikipedia, straight from Wikipedia, and it says, BDDs can be used for private information retrieval. And I had to look that up, and I said, what is private information retrieval? This is where a user can retrieve data from a server without revealing which item it received. That's kind of interesting, where you get something from the server, but nobody can tell which one you got, so it's private, which is kind of neat. Yeah?
Including the server?
I guess so, including the server. I mean, it's got to find it somehow, but maybe it finds it and then returns you something based on some key, and it doesn't know which one it actually returned you. I don't know. I know it's cool. I don't know any details, and I don't know how binary decision diagrams are used there, but it kind of sounds like a cool opportunity to look into it. So maybe I'll do that. All right. So that is binary decision diagrams in like half an hour instead of an hour and 41 minutes from Donald Knuth. Anybody have any questions on that? I'll have to think about the types of questions I can ask you about this. It won't be too taxing, I hope. All right. Anything else? All right. See you guys Wednesday. Oh, for lab, by the way, in lab for the first 10 minutes or so, if you could fill out the, did everybody get the email about Trunk having the